We're now going to consider the centre of mass, but before we get into the mathematics of how to calculate it, let's consider why it's useful to know where the centre of mass of a system is. So the centre of mass of a system is the point that moves as though all the system's mass was concentrated there, and as though all external forces were applied there. So when we were throwing a ball before, we were modelling the ball as though it was a point mass moving about the centre of the ball, which makes sense for the ball. But that centre of the ball is actually the centre of mass of the ball. So as long as the ball's symmetric, then the centre of mass will be in the middle. Now, the same thing actually applies to a stick, which can be a little bit more complicated. So physically, to find the centre of mass of a physical system, what we can do is find the point about which the system balances, if we place it on that point, or we can try hanging it, and the point about which it will hang levelly, which can be a little bit tricky to find, is the centre of mass of the system. So for this stick, you can see the centre of mass is just at the end of the yellow point there. So hopefully you can see that clearly. Now, if I were to throw the stick so that it undergoes projectile motion, it will rotate, but the centre of mass should move as a nice projectile. So let's have a look at that. With this stick, it has been weighted, so one end is heavy and the rest is all made of wood. Okay, let's look at it as it's thrown. So now we know why the centre of mass is useful, let's have a look at how to calculate it. We'll start with simple cases and then we'll move up to more complex ones. So let's start by considering a one-dimensional system made up of discrete particles, so a series of dots with different masses along a straight line. The formula to calculate the centre of mass in this case is x centre of mass, so we'll present centre of mass with a little subscript, COM, and x because it's a position. So that is equal to the sum of xi mi divided by the sum of mi. So in this case, xi represents the displacement of the ith particle from the origin, and mi is the mass of the ith particle. When we sum all the masses, so the sum of mi, we're just getting the total mass of the system. So often we'll represent the total mass of the system with a capital M. So we could also write that xcom is equal to the sum of xi mi all over capital M. So let's have a look now at how we can apply this to a very simple problem. So we'll start with just 2-point masses. So the question is, find the centre of mass of the Earth-Moon system. The Earth is 3.844 times 10 to the 8 metres from the Moon, and it's measured from centre of mass to centre of mass. So always assume that measurements are given from centre of mass to centre of mass. The Earth has a mass of 5.972 times 10 to the 24 kilograms, and the Moon has a mass of 7.3848 times 10 to the 22 kilograms. Okay, so in order to solve this is a one-dimensional case because here we've got our Earth, here we've got a Moon. So it's useful to start by drawing a diagram. And let's measure x from the centre of the Earth. So let's put this as x equals 0, and then we've got this distance here, and we're told that this is equal to 3.844 times 10 to the 8 metres. So that distance is xm, and we'll call x of the Earth is equal to 0. So the formula we need to use is that the location of the centre of mass is equal to the sum of xi mi over the sum of mi. So in this case, we are only considering two objects, the Earth and the Moon. So we'll give them subscripts E and M. So what this formula means is that the x of the Earth times the mass of the Earth plus the x of the Moon times the mass of the Moon
over the sum of the masses, so that's the mass of the Earth plus the mass of the Moon. And we've just said that x of the Earth is equal to 0. So this one here is 0, and this distance here is x of the Moon, because that's the distance of the centre of mass of the Moon from the centre of the Earth, which is our origin. So what we can do is we can now substitute in. This first term's 0, so we won't bother writing down the mass of the Earth here because we've got a 0 to start with, plus xm, which is 3.844 times 10 to the 8 times the mass of the Moon. So the mass of the Moon is 7.3848 times 10 to the 22. And then we divide it by the total mass of the system, which is the mass of the Earth, which is 5.972 times 10 to the 24, plus the mass of the Moon, 7.3848 times 10 to the 22. So you can see the mass of the Earth is almost 100 times bigger than the mass of the Moon. Okay, so now what we can do is we can enter this into the calculator and solve it. And when we do that, we get 4,695,316 meters. If we divide it by 1,000, it'll be in kilometers. So that's 4,695 kilometers. And let's give it to 4 significant figures, because the Earth-Moon distance up here is given with 4 significant figures. Okay, so interestingly, the radius of the Earth is equal to 6,378 kilometers. So this center of mass is actually inside the Earth. So it's around about here where I've drawn the purple cross. Now, that's not really surprising because the Moon, it has so much less mass than the Earth. So we'd expect that center of mass to be much, much closer to the Earth than to the Moon.